Hello everybody. This video is going to be covering material for the brand new course, Principles of Biomedical Science. Now, I want to be completely clear. This is a brand new course. I was not a student when this course came out. However, I have individuals sending me the materials that the professors are using and going through the materials and all of the concepts and much of what is included in this are obviously concepts that apply later on to the program that I'm extremely familiar with. So this first week, talking about the fundamentals of physics and applications to human biomechanics. Now, I love physics. I kind of wish I had taken more physics courses in my undergraduate career, but physics 1, 2, and then laboratories were enough for me at that time. But it's really cool concept because understanding physics, and my undergraduate is exercise science, so I took a lot of physics and kinesiology courses focusing on the biomechanics of in movement. So it was nice to kind of get back to my roots a little bit with this material. So let's jump right in. So learning objectives for this week, we're going to look at calculating vector forces and describing their significance. We'll look at torque and mechanical equilibrium, applying torque to human biomechanics, and then also applying the physical principles to different clinical scenarios like muscle actions, posture, stability, and also rehab exercises. Now, to be completely frank, going through all of this, the last three objectives seem like they're more of an afterthought in all of this, but we will talk about them, and I might go into a little bit more detail, kind of things that I think are more important for you to know for the long term. Okay, so first off, scalar versus vector. So scalar is our typical, our standard, our normal numbers, the things that we think about. So temperature, mass, time, speed, the magnitude component only. There's no direction involved. It's usually just a single number with a single unit, and that's it. We're good to go. So this is something that you can physically go out there and measure super simply using, a scale, using a ruler, using whatever. A vector is a mathematical term that we talk about, and we use it to represent both a number as well as a direction. So you can think of this, for example, like, oh, I'm in my car going 35 miles per hour heading north. Those two things combined, the 35 miles per hour plus the direction, that makes it a vector. So you add both of those components, or for example, if I were to say, I am walking forwards, or if I'm going to take 5 steps to the right, the combination of a magnitude, so a number, an amount, plus a direction, that gives us the vector. And we represent that with these little arrows. Okay, the length of the arrow, or so how long the arrow is, that is referring to the magnitude. So if we want to make this, if we look at this kind of broken down a little bit, this would be, we could call this 1. Double it, that's 2. There's a value of 3. There's a value of 4, and so on. It's all relative. You draw the vector relative to whatever it is that you are specifically doing, but that's what the length of the vector represents. Now, the actual arrowhead, that represents that direction, that that north, the upward, to the right, downwards, whatever direction it is that we're actually traveling, whatever that direction we're actually moving. And so with vectors, we typically will have a force. Typically, we're not moving in just one direction. A lot of life happens in the diagonal. So we're moving, we're not just moving north, we're moving northeast or northwest. And so that diagonal, we want to be able to figure out, okay, how do we get all the way there, right? How are we going diagonal? Or what if we want to add some of these values together? So there are different ways that we can add and subtract vectors as well, using them just like we would numbers, but also taking into account the direction. So the way that I like to think about vectors is like you're taking steps in a couple of different directions. So for example, imagine that I were to take 2 big steps diagonally and I end up in a specific location. I go back to the start where I started. There's other ways that I could get to that exact same spot. Instead of stepping diagonally, I could step to the side and then I could walk forward. So when we talk about vectors, we can always break them down into what you could call their base components, their basic components. There, when we talk about directions, there are 3 directions that we consider. We consider, one sec, my cat is chewing on my computer cords. Oh. One of her favorite activities is when I'm trying to record, she loves to chew on everything. Okay. When we talk about planes of movement, you'll see this eventually. You can make this little hand position like this, the thumb up, pointer finger extended, middle finger straight out. And these represents our different axes. Straight up and down, that's our y-axis. Across, left and right is our x-axis. Forwards and backwards is our z-axis. Those are the directions that movement occurs. Obviously, we can have a combination of those, but those are all the axes that we talk about. We're going to start by showing we can break down our vectors into x and y components. Okay? So, for example, this one right here, which of the vectors best represents the sum of vectors 1 and 2? So vector 1 is just going to the left. So we say, okay, which axis does that relate to? That's our x-axis. So we say, okay, it's to the left with the x-axis. Vector 2 is going down and to the right. So it has an x component because it's going to the right, but it also has a y component because it is going down. Remember, so up and down is y, left and right is x. So what we can do, just like thinking about, those steps, we could walk diagonally to get to that spot, or we could do a couple steps sideways and then a couple steps forward. That's essentially what we draw. We say, okay, in order to match this, we go down and then across. And then we can take those and we can add them together based on their directions. So you thinking about this like steps, this one right here, this one is longer than this one right here. In actual cases where you have to do the calculations, they're going to give you the values. And so don't worry, like this is just kind of representation. We're going to give these some fake values right now just for make it a little easier. So let's call this 4 and let's call this 2. Okay, so it has a value of 4, a value of 2, because this is about twice as long as this one down here. So 4 to the left and 2 to the right. So we add those together. Let's talk about them in forms of steps. If I take 4 steps to the left and then 2 steps to the right, how many, like where do I end up? It's the same as if I was taking 2 steps to the left. So my x direction, my x-axis direction, is going to be leftwards. And then we would add, okay, anything that's in the y-axis. Number 1 doesn't have anything in the y-axis. Number 2 goes down. So we're looking for down and left, which would give us a diagonal arrow down and to the left, which is our B value right here. And you can do the same exact thing with subtraction. So we could take these, instead of adding these, we could say, okay, we subtract them, and essentially you just make one of these negative. So it works a little bit differently. Most of the time, you're not subtracting vectors. It's a little bit weird to think about subtracting vectors, especially in the form of biomechanics. But the tip that you do is that you take the whatever vector you're subtracting, and you flip it and make it negative instead. And so you flip the directions. So if I were to instead do the subtraction, so 1 minus 2, we could flip the directions of 2. So right now it's going down and to the right. We would completely reverse it, and instead it would be going up and to the left. And so then we could add it. We have our x value here. We have our y value of that here. We add those together. So now we have 2 steps to the left plus 4 steps to the left. That gives us 6 steps to the left. So huge arrow to the left. And instead of going down, we're going up. So that would look more like our d value right there. Vectors can be a little bit confusing at first. I recommend playing with them just a little bit. Looking at these, a lot of physics, it's just math. So it's going to be understand the equations, understand the steps, and as you do the steps, you're going to be able to get the correct answer, and eventually the understanding component of it will click. If we can't get the understanding component to click, at least we're going to get the math right. That way we can get the answer correct and do well on the test and give ourselves some more time to understand that material. So what if we're dealing with actual numbers though? So once we start dealing with real numbers, it gets even easier because we have formulas, equations that can immediately tell us what those numbers are. What is our actual value? Instead of using, like I just used, the steps, what are the actual numbers that we can get? And we do that with these equations. So the force in the x direction, so if we have a diagonal direction, the force in the x direction equals the total force multiplied by cosine of this symbol is called theta. Theta just means the angle. So it's the cosine of the angle of the force compared to the ground. So right here, here's our theta value from parallel to the x-axis. How many degrees up is it? So that's our x force is, in this case, this practice question was you have 10 newtons at 45 degrees in the direction of the arrow. So we plug in our numbers. The force is 10 newtons. The cosine is of 45 degrees. And we would just plug those into the calculator. It'll give us our values, and then we can answer the questions. It's as simple as that. We don't want to make this too complicated and try and overthink it. All right? Now, why do vectors matter? Why is all this important? It has to do with the chiropractic adjustment. All of our joints in our body have very specific joints that line up a certain way. So there's an angle between all the joints, especially in the spine. The cervical spine is a roughly 45-degree angle where the facet joints meet each other. And then it changes as you go down the spine and the thoracic and into the lumbars. And so the way that you adjust them is going to change, and the direction that you're going to adjust is going to change. And this is super, super important. With chiropractic, we call this the line of drive, the direction that you are pushing your force through. And this is critical for us as chiropractors to understand, hey, when I'm putting a force, when I'm introducing a magnitude and a direction into this specific spot, I want to make sure that it's complementing the natural structure of the vertebrae or of the joint. I don't want to be fighting it. I don't want to jam the two sides of the joint together. One, because that could hurt, and two, because that could actually make things worse. So we want to make sure that we're lining up and our vector, the direction and the magnitude of force that we're applying, goes in the right direction so that you get a nice sliding of the joints on top of each other. And that's what gives us a really I would call a clean and a very nice adjustment, is paying attention to that line of drive and to that direction. You were going to have this beat into you over the course of the program. All of your adjusting courses, you're going to be made to memorize the lines of drive, but I want you to think about them a little bit more. And this is one thing that's really, really good to practice, especially as you start getting into palpation courses. Eventually, try 2, try 3 when you come into campus in person, and you start to you learn what joint play is, where you can kind of press on the joint and feel where, okay, this angle joint kind of catches, but switch up the angle a little bit, and this joint is nice and soft and spongy and moves nicely. There's no smashing together of the joints. That's why this is all important, why we understand the specific forces, because if we're off on the force, we're sending force into other parts of the joint that we might not necessarily want to be sending force into. We want to be specific when we adjust. Now, we can continue this. You can add as many vectors as you want together. And so it can continue to get a little bit more complicated, where let's say this right here, we're adding vector A and vector B together and we want to calculate vector R. That's right here. It's the exact same process that we did before. Break both of these down into their X and Y components. Their X direction and the Y direction, how many steps does it take to get to equal that diagonal value? How many steps does it take right and up, or left and down, or whatever the direction the vector is? And then you just add those together. The 4 or 5 right steps here from the A, and the 1 step from the B, and then the 2 steps here at the A, and the 4 steps from the B. We add all of those up, and if we look at this, we actually get, if we move this one over to this side, we get a right triangle. And again, we need to just plug and chug into an equation. You can use Pythagorean's theorem. The Pythagorean's theorem is a squared plus b squared equals c squared. So a being the x direction, b being the y direction, c being the hypotenuse, the diagonal direction. So again, we whip out our calculators, we plug in the numbers, a squared, b squared, we plug in the a value, plug in the b value, square root the whole thing, and we come out with the answer of what our force is going to be. Now, I mentioned earlier, we actually have 3 planes, right? So we're going to get a little bit more complex. And continuing to add into that, we have a 3rd plane. That's the z plane. So z is forwards and backwards. X is left and right. Y is up and down. And again, we just have a nice, neat formula in order to figure this all out. They're going to be giving you these values. The meanest that they could possibly be is they would combine the x and the y values, and they want you to use the sine cosine to solve for those and then plug it in with the z value. Okay, they're not going to make you do a crap ton of math just to get these answers, because again, we're not mathematicians, we're chiropractors. But the point is, it's the same thing. We have an equation. So right here, this is the absolute value. So that means it automatically becomes a positive number. The absolute value of the force equals the square root of the force in the x direction squared plus the force in the y direction squared plus the force in the z direction squared. So right here, for this one, we have -20 is our x direction. Plug that in. 50 in our y, 500 in our z. We plug all of those values in, square them. We take the square root. We say, oh, what's our number? We do all of the math. we end up with 503.29 newtons. So 503 is that total force that we are delivering. I know why they included this slide in here. Heart vectors, they're in Physiology 1, in Try 2, you will talk about the heart, you'll talk about EKGs or ECGs, means the same thing, just depends on which person you're talking to, which term they prefer to use, and something that's called the mean electrical axis. I'm not going to go too deep into this because this is going to be Physiology 1, but the introduction to this concept is super important. When we take an ECG of the heart, it's an electrocardiogram. What we're measuring is the electrical signal that's flowing through the heart. And we're measuring the magnitude of the signal, how much signal is there, and the direction of that signal. We want it to be going in a very specific direction. When you take an ECG, you take a bunch of these little electrode stickers and stick them all over different parts of the body. And the machine measures electrical current in all the different directions. And it gives us these values. We call these leads. So the leads tell us the electrical current that's happening in different directions. Lead number 2 is our go-to. We like lead 2. Lead 2, this is roughly our normal value. This is what a healthy heart should be. This is the direction that electricity should be flowing in a healthy heart. If it's not flowing that way, it can be for a number of reasons. When we have somebody has a heart attack, or they're having ischemia, so they're not getting enough blood to the heart, the muscles don't work quite properly, or muscle could be dead. Dead muscle doesn't have electrical current in it. So then we get skewing of the mean electrical axis. We get skewing of the direction of the electrical current. Or if the heart's working way too hard because, let's say, we have high blood pressure or we have an issue with one of our valves. As a result, the muscle gets bigger, and so then we have more electricity, we have more magnitude, so that can change the overall direction of our electricity in our heart. So main concept to understand, mean electrical axis tells us the direction of flow, the vector of flow, the direction and magnitude of flow of electricity through the heart. We want it to go towards lead 2. And if it's not going that direction, we have some issues. Okay? And there are lots of other forces to consider. Again, this isn't like a full-blown physics course, so we're not going to get into all of that. But obviously, like when you push into something, there are other forces all around. There's friction and a bunch of other things. We talk about Newton's 3 laws. The first law is known as the law of inertia. So an object at rest will remain at rest unless you act on it. As well, an object in motion will continue unless acted on by a different force. This is just kind of raw memorize-y. They're going to ask you a question. They're probably going to throw a question in, basically, which of the following is Newton's first law or second law or third law? And you need to match which law is which in order to get your points. So we want to know the 3 different laws. First law is law of inertia. If you don't touch an object, it's not going to move. Once you start moving it, it prefers to move unless it gets acted on by a different force. Newton's second law is the law of acceleration. So it depends on the mass of the object and the amount of force applied. We'll see this equation in just a minute. Force equals mass times acceleration. We'll use that a couple of different times. Finally, Newton's third law, for every action, there is a reaction that is equal and opposite in direction. So for example, if I slam my foot on the floor, I'm putting force into the floor, and the floor is emitting the same amount of force back up into me. Those are our 3 laws. This is just a fun little question. This is a question that just don't think too hard. The answer is what the answer is. If you try and go too deep into it, your brain will start to be like, what the heck? Basically, if you're spinning something around and you're on a rope over your head and the rope snaps, it's going to continue to go straight forward wherever it broke off. It's not going to continue in a circle. It's going to follow a straight line path. Don't overthink it. Don't think about it too much. It gets a little bit confusing if you kind of go down that rabbit hole. Some more practice questions. This is talking about that equation that we looked at. The Newton's second law relates force and acceleration. So you can have a couple of questions where they'll give you the mass and they'll give you the force, or they'll give you the acceleration and they want you to calculate it all. This is just showing the relation between all of these different things. Our acceleration depends on how much force we put into something and how much mass it has. It's kind of like if you compare, like if you're playing tackle football and 100-pound cornerback tries to tackle you versus the 400-pound offensive center. Which one is going to hit more, right? The center is going to hit more because it has way more mass. They're going to have similar-ish accelerations. So the larger mass has a much greater force. So that's kind of that whole connection. Again, just plug and chug. There are a bunch of different types of forces. I can see several questions being pulled from this. If you're not aware, all of this stuff that's down here, I guarantee you is ChatGPT generated. 100%. I know that because I know the font. I know the way that ChatGPT tends to word things. So if I had to guess, I would say more than likely there's a lot more information down here than you truly need. What I would recommend, I would start with what is on the actual slides. Understand these. So I would know which of the forces are the contact forces, which of the forces are at a distance forces. Then if you have more time, look at, okay, which forces are created inside of objects, which ones decrease at distance. And then from there, continue. And if you want to learn each individual definition, that's also probably a good idea. That'll probably be what takes you, from that B to that A- range when you get into exam time. Talking about the actual human body, forces in human movement, you get push and pull forces. That's everything that there is. I should clarify, all of our muscles pull. Not a single muscle pushes. All of our movements, everything is based off of the muscles shortening and pulling the bones. That's what allows us to move. We get push forces when we interact with other stuff around us. We push a ball, we push a box, we push against the wall, we push up, all of those things. Muscles are going to pull, they're going to shorten to create a force. The professor goes a little bit into what is called isotonic contraction. Iso means same, tonic means tone, so maintaining the same tone with a contraction. This is usually refers to activities where we're not changing our acceleration or our speed. We're just doing something constant. So the whole process of torque, there's not a lot to torque. What we really want to understand is this is how we move. The fulcrum or the axis, this represents our joint, specifically where our joint is located. And then the moment arm distance, that represents the bone. They can call it moment arm, they can call it lever arm. That's our bone. And then the force that gets generated is from our muscle. So the muscle is going to generate a force, which causes a rotation around the fulcrum. And that's how we are going to get movement. Now, our muscles and everything set up is not perfect. So we're not going to always have, perfectly perpendicular forces. We're going to have forces happening at a little bit of an angle. When things happen at an angle, it slightly decreases the lever arm, aka that moment arm, and changes the force, because now we have a y component and an x component, so it changes the overall force. So it's just something to understand. That'll be a test question somewhere, where what happens when you have an angled LOA, that's called line of action. That's the overall force, the direction of the force. So what happens when you change that, or you angle it a little bit, you get a shorter lever arm, therefore you produce less torque. This is something, for example, a really important joint to consider is the knee joint. That's actually why we have the patella. We have the patella to actually increase the angle from the muscles that are connecting our quadriceps, that are connecting all the way up at the very, very top of the leg. So that when they can go and they can come down and connect into the tibia, it increases that the line of action. It increases that angle to allow us to move our knee with stronger force, with greater torque. So that's why we actually have the patella and the quadriceps tendon. Another equation, so there's lots of different ways to write the same equation. Torque is force multiplied by the moment arm distance, or it can be the force multiplied by what's called the perpendicular distance to the line of action. So it's the same thing as saying the moment arm, just different words. So again, it's going to give you values and you calculate them out. And the understanding is that within biomechanics, with posture and stability, when we are holding still, it's not that none of our muscles are active, it's that our muscles are at equilibrium. So we constantly have gravity acting on us. So we need certain muscles to be able to keep us up. One of those being, for the skull, our faces are a little top heavy. That's why looking down is easier than looking up. So we constantly have posture muscles being activated in towards the back in order to keep us at what's called equilibrium, keeping us stable, keeping us non-moving. So so we get a sum of forces when we're not moving. The sum of all the forces is 0. Sum of all the torques is also 0. There's a bunch of vocab down here: posture, stability, center of gravity, line of gravity, torque, and equilibrium. Some of these points, very important when it comes to chiropractic, like center of gravity. This is where all of our force, like where the center of us is, so our force is being primarily located, going directly down towards the ground. And that becomes important when we start talking about adjusting somebody, because you want to use physics to your advantage when you go to adjust. So, but you'll talk about that more in the future. Yeah, so being at equilibrium, balance of forces and torques are all 0. For example, the example of forces on the arm during a bicep curl, if you're maintaining that one position, you're holding it right there, you're in equilibrium. The amount of force being generated by your bicep is equal to the force of that physics textbook sitting in your hand, pushing downwards. And that wraps up most of all of this whole first kind of chunk. I pointed out some of the most important things. My biggest recommendation is with everything, every single one of your courses, the best strategy is to attack the first week, or I should say the first lecture exam material, really, really, really learn it, really, really get a good solid hold of it. So that way you can learn how the professor asks questions. So if you can learn how the professor likes to ask questions, you're in a much better position to know then, okay, what do I study? What do I prepare for? On top of that, if the professor comes out with a study guide, I'll do my best to get a hold of that and kind of run through that again as well, and post a video here kind of going over that and going over the most important components. Everybody, thank you so much for watching. If you haven't, please subscribe to the channel. It helps out a lot. Leave a like on the video. As well, what allows me to keep on doing all of this and continue to grow is down in the description below. I have actually a forms link that you can fill out in order to get access to all of my study materials. Like I've been out of school for 4 months, 5 months now. I'm working, I'm treating patients, I'm doing all these things, but I'm still, this is my passion project where I'm continuing to create content to hopefully make life a little bit easier for the next generation of chiropractic students. Have a wonderful day and good luck studying.